Hey guys, welcome to Safi Mixed. In this video, I want to derive a relation for the variance of Poisson distribution. We know the variance of a random variable in a distribution is given by sigma square equals sum over n equals 0 to infinity n minus n bar whole square p of n. This is a general definition for finding the variance of a probability distribution P of n for a random variable n, where n bar is in fact the mean of the distribution. And this relation can straightforwardly be reduced to average of the square of random variable minus square of the average of the random variable. And if you don't know about this extraction or this form of the variance of a probability distribution of a random variable, I would suggest you to watch the video on the link in the description of this video, where I prove the relation, this form of the variance from this form. So in order to find the variance, I just need to find this thing, and you will see only this thing would let us know about the variance. So I call this equation 1. And I want to find the average of the square of random variable. And we know that the average of anything in a probability distribution is given by the square n is in fact given by n equals 0 to infinity n squared p of n, where p of n is Poisson distribution, and we know the form of the Poisson distribution. It is given by p of n equals the average power n divided by n factorial exponent minus n of average, n average. So this is the definition of Poisson distribution. I just want to put this value at this position. That would let me find n squared in the form of n equals 0 to infinity n squared into n bar to the power n divided by n factorial and exponent minus n bar. Okay, I can take this to the left of the summation because this is independent of the summing parameter, and I split this one into two factors, that is n times n, and similarly I factorize this into two terms, and I make a change over here, and the whole I do like this: exponent minus n average somewhere n equals 0 to infinity n times n, and here I take n average n minus 1 times n average, that is I add a 1 and subtract a 1 in the power of n and then separate them, and then I write n into n minus 1 factorial. That is, I can factorize n factorial into n minus 1. I cancel one of the n in the numerator with the 1 in denominator, and again I can take this thing to the left of the sum because this is independent of it, and therefore I write this as n bar exponent minus n bar sum over n equals 0 to infinity n, and this becomes n bar raised to the power n minus 1 divided by n minus 1 factorial. And you see, when n is equal to 0, I multiply 0 over here, so that the whole term is 0. Therefore, I can remove the n is equal to 0 terms from the summation, and then doing that, I can rewrite this in the form n bar squared equals n bar exponent minus n bar and then sum over n equals 1 to infinity n and one thing more, I want to add a 1 to this term and subtract a 1 to this term to write it like this: minus 1 plus 1, and then n bar raised to the power n minus 1 divided by n minus 1 factorial. Okay, now again I can split this summation into two summations, one for n minus 1 and the other just for 1, and doing that I can rewrite this relation as n bar exponent minus n bar the whole multiplied with sum over n equals 1 to infinity n minus 1 times n bar power n minus 1 divided by n minus 1 factorial. I'm writing this summation for n minus 1, and then again I separate the one part to write it like this. I'm writing this over here plus sum over n minus 1 to infinity n bar raised to the power n minus 1 divided by n minus 1 factorial, and that multiplied with these two terms. Now let us look at the first term inside the brackets. For n equal to 1, this term goes to 0, so I remove that term from this summation and rewrite the summation in the form n bar exponent minus n bar sum over n equals 2 to infinity, because n equal to 1 is 0, so I drop that term, and then I write this as n minus 1, and what I do, I want to make a change over here, that I write as n bar n minus 2 times n bar, that is I'm adding minus 1, I'm subtracting minus 1 and then adding plus 1, so the plus 1 term I'm writing over here and the minus 1 term I add to this to make it n minus 2, and similarly I factorize this n minus 1 factorial into n minus 1 into n minus 2 factorial, writing it like that, and then I write the second term as it is, n equals 1 to infinity n bar raised to the power n minus 1 divided by n minus 1 factorial. Okay, I can cancel this n minus 1 with this one in the denominator, and I can take that n bar to the left of this summation, and I rewrite this relation in the form n bar exponent minus n bar. I'm taking that to this side to write it over here n bar, and then the summation n equals 2 to infinity n bar raised to the power n minus 2 divided by n minus 2 factorial, and then I write the second term as it is, that is n equals 1 to infinity n bar raised to the power n minus 1 divided by n minus 1 factorial, and then I close the bracket. Now I want to reparameterize the summation parameter in these two sums. In one case I define over here that m equals n minus 2, and this implies that when n equal to 2, then m equals 0. And similarly, when n tends to infinity, this defines that m also tends to infinity. And for the second, I define another random variable kappa k, which is equal to n minus 1. And again, to fix the limits, when n equals 1, this equation tells that k equals 0. So this implies that for n equal 1, k is 0. And for n equal to infinity, obviously k goes to infinity. Therefore, the upper limits of both the sums remain the same. And I rewrite that relation in the form n bar square equals n bar exponent minus n bar, and this will become n bar, then sum over m equals 0 to infinity n bar raised to the power m divided by m factorial and plus sum over k equals 0 to infinity n bar power k divided by k factorial. And now, using the Taylor expansion, we see that this thing corresponds to exponent n bar and this thing corresponds to exponent n bar. That is, we see that sum over m equals 0 to infinity n bar raised to the power m divided by m factorial equals sum over k equals 0 to infinity n bar power k divided by k factorial. They both equals exponent n bar. So if I replace this value at these two positions, then I write n bar squared equals this thing, n bar exponent minus n bar, inside the bracket this n bar, then this is exponent, this is exponent, so I write exponent n bar plus exponent n bar. Or from these two terms, I take the n bar common to write it n plus 1 times exponent n bar. And now I can combine this n bar with this exponent minus n bar, and if I combine them in a single exponent, I write them as n bar into n bar plus 1 into exponent 0, or I write n bar squared plus n bar. So n bar whole square is in fact equal to square of the average of n plus average of n. And now if I replace this value of n bar square in this one equation, I can then write things like this, that is sigma squared equals n bar squared plus n bar. It is the value of this thing from this equation, and then I'm writing that n bar squared. This cancels with this, and we are left with n bar. That is, the variance of Poisson distribution is exactly equal to the mean of Poisson distribution. And we have already proven that this mean is also the mean of binomial distribution. So we can say that the variance of Poisson distribution equals to the mean of Poisson distribution, or the variance of Poisson distribution equals the mean of binomial distribution. And if you haven't yet subscribed to Safi Mixed, kindly support the channel by pressing the subscribe button. Thanks for watching.